on the Java track will be Rafael. Rafael, you can Rafael Winterhalter. Is that the right pronunciation? It's German.
It's really good. It's German, yeah. So I'm German, but I live in Norway.
So Winterhalter?
Winterhalter, yeah. That's good.
Well, sometimes my high school German comes back a little. Anyway, without further ado, it's 1:15. I want to give the stage to Rafael. If you can share your screen, I will blend it in for you. Give it a go.
Absolutely. Just share my screen here. And
yes,
here we go.
I see your screen coming up. I will mingle it in, and we see it over there. Let's go.
All right. So yeah, thanks for having me, first of all. Glad to be at the conference again. I'm starting to miss it. And it's good we can come together and collect some money for the VHO now that it's very needed, I guess, more than before. I'm giving a talk I was supposed to give pretty soon, again, about Java agents, which is what I work with the most. I'm the author behind a library called Byte Buddy, which is mainly meant for code manipulation and generation, and also for Java agent generation. And what I want to do today with you in this half an hour, as you see from the title, I can't do the definitive guide to Java agents, but an introductory one. I want to explain to you what Java agents are, also explain to you what they can do and what they are used for. I'm sure any of you has used the Java agent in some regards before. I try to create an understanding of what they can do, what they do, and what kind of implications that has for the applications you run and how you can develop one yourself. So we start with the most basic question, which is, what is a Java agent? And a Java agent is nothing more like if you consider a main method. We all know that's an entry point to a Java application. A Java agent is basically an extension of this entry mechanism. So while we can specify a main class in any jar file, a Java agent is the same more or less, but instead of specifying a main class with a main method, you specify a pre-main class with a pre-main method. And by running this pre-main method, you can basically extend any Java program by additional code. But you can deliver this agent as an additional artifact, so it doesn't have to be blended with the application you actually write. And this is why it's popular with tool vendors. So basically, you can add something to your application that, for example, monitors something, or add some logging, some setup of some sort, without having to compile these two artifacts together. And you can have several of those. They will just be executed in the order you specify them. An even more advanced way of using Java agents, however, is to specify so-called dynamic agents, where you can take a running Java process and you can enrich this already executing Java process while it is running with additional code. And again, you just create a jar file. You have some class where you implement a public static void agent main method and add a manifest entry that says agent class and points to that class that contains this method. And then you can tell the JVM to basically load an additional jar file while it is running and to execute additional code. And again, you can have more of those, and those will just run in its own thread until they complete and in parallel to the program. And this is how a lot of modern tooling just scans, for example, for Java virtual machine process IDs, finds these processes and enriches them without your explicit doing. So you can develop some tooling based on that, and for example, look into a JVM when it's starting to crash and explore things despite not having known this demand when you started your JVM. So basically, this is what Java agents are, and there's no big magic to it. It's a standard feature that the JVM has supported since Java 5 in a fairly basic manner, but it has supported it very comprehensively since Java 6. And ever since, the tooling space for the JVM has grown by a lot, and this is why you get a lot of good tooling for the Java virtual machine that you cannot find for other platforms, because it is very easy to write these programs. And hopefully after this talk, you can start writing your own small tools. Right, so how does a static Java agent, one that you specify as a pre-main method, look like? It can look like that, as simple as that. So if you write this pre-entry class and you write a pre-main method in it, you can just print some argument. And of course, this is a hello world example of a Java agent. This isn't very useful in itself, but you can potentially imagine how this can be useful in a context. For example, let's say you want to set up some configuration based on environment variables, and you don't want to hard code this into your application because it only affects a certain runtime environment. Then you can implement the setup once as a Java agent, and you can just prepend it to any application you run in this environment and map, for example, environment variable names to system properties that you need to set. So that will be a simple application, right? And the dynamic agent is much harder to do. Of course, now you don't specify it when you run the Java main method, but at a later point in time, the JVM contains a special virtual machine API for that. You just tell this API what the PID is of the Java process. Then you tell it to load some jar file with some argument, and it will be loaded, right? So you can do this from some other process on the same machine. And as long as it's owned, as long as your process is owned by the same user, you can inject this jar file into any virtual machine, more or less. And for example, if you use JVisualVM, if you ever wondered how JVisualVM can look into a running Java process, it will do exactly that. You will tell JVisualVM what PID you want to connect to. It will have a Java agent placed somewhere and on the file system of your machine. And if you're logged in as the same user as this Java process that you want to monitor with JVisualVM, you can do so by attaching the JVisualVM agent, and it will then basically display data that the agent sends back to the graphical user interface. This is how all the tooling works in the JVM, more or less. And also more advanced in commercial tooling, of course, basis of that. So, so far so good. Now we know how you implement a Java agent or what a Java agent is. And technically you can now already run code in a foreign JVM process, but this is not what makes Java agents exciting. So we've seen in the last slide that Java agent takes a single argument of type string that contains the argument that you provide to this agent. So you tell the Java agent, for example, that you want to print my agent as hello world example or something else. But you can also supply a second optional argument that you can specify but you don't have to, and this type of argument has to be of instrumentation. And instrumentation is basically an interface that implements a lot of low-level functionality access for the JVM. And the most interesting one is probably the possibility of registering a class file transformer. A class file transformer is an interface that implements a single method where whenever a class is loaded in the Java virtual machine, you will be receiving a callback from the Java virtual machine with the possibility to transform the class. This is, of course, useful if you, for example, want to write monitoring services. So you, for example, want to change a class that implements some method to always extract some data to Prometheus, for example. Then you can, instead of hard coding this into the method in question, you can just tell the JVM that you want to be notified whenever a class is loaded, and then basically change the class that you actually load to include your enriched behavior. Because a Java class file is more or less nothing more than a byte array, right? So all you need to do is you have to find the bytes in question that have this particular meaning you want to change, and then you can adjust the behavior of any class that exists in a JVM, right? And the same you can do also with a dynamic agent, but the problem with a dynamic agent is that you don't know when you attach to the JVM. So potentially classes are already loaded when you install your class file transformer. But fortunately, the JVM cannot only transform classes, it is also capable of retransforming classes that have already loaded. So you can actually change the behavior of a Java application completely while it's executing. And this gives you a possibility to not even delay the startup of an app, for example. If you want to monitor, you can just attach in parallel and then basically patch the Java virtual machine to do what you need to do, right? All you need to do is you have to provide a second argument here with telling the JVM that you actually do want to retransform, and then you have to tell it what classes those are. All right, so how does this work? You all know that when you compile a Java source code file, this is translated into a Java class file. And you've seen these class files, those are packed and packaged together into a jar file where they then still exist, and you can look at those. Java class files are very, very similar to Java source files in the content they provide. They just display it in a more machine-friendly manner, but they don't do any big transformations or performance optimizations. It's only at runtime, when the Java virtual machine executes your code, that these class files, which are more or less byte arrays, are compiled to machine code. So what you can do is that you can take these class files at runtime, where they are represented as byte arrays, and you basically adjust this byte array by adding a few instructions to display the behavior that you want to display. So for example, if you invoke a method, then this method call will have a certain byte placed in the bytecode at a particular location. And if you look up the Java virtual machine specification, it specifies what byte in this byte array means what. And by knowing that, since the Java virtual machine specification is very precise and very well maintained, you can reliably transform any code that you want to transform. Right. But of course, it's a bit of an effort to understand all this, and this is why people like me create libraries like Byte Buddy, which hopefully make this deep understanding of Java bytecode obsolete to you, where you can then rather focus on the actual logic that you want to implement. But before I show you what, I try to show you two real-world examples of Java agents that I hope everybody has encountered in some way in their career, to explain to you or make you understand why this is actually something that we use every day, more or less. So as a first example, take the Mockito library. For years, we've been just subclassing any of your classes to create mocks. So we have created mocks in Mockito by just taking your class and by subclassing it and overriding all of its methods. And the overriding methods, we can make use of virtual dispatch, and then of course change the behavior by these overrides. So we have used Byte Buddy, for instance, to create subclasses, and then these subclasses were the representation of the mocks. But in recent years, or the recent 2 years, we have started to use Java agents for that when Kotlin came along and became popular. And the reason for that is that Kotlin defines final classes by default with final methods, where this approach didn't work anymore. And there was, of course, a demand in mocking Kotlin classes. So since we are running Java and we can use agents, what we do is we attach a Java agent to our own Java process. And then what we do is we take your class that you want to mock, and we inline the mock into the method you wanna be able to mock, right? So by inlining the code, by basically representing your class file as a byte array again, finding the location of your method in this byte array, and then adding a few lines of code in the beginning of every method, we can then check within the method if we are currently a mocked instance and then apply the mocking logic, or if you're not a mocked instance, if you apply the regular logic. And this works then without you noticing, and it works with final classes and final methods, and it's been pretty well adopted in the Java space. Another application, I can just tell the example of a monitoring tool I've been working with for a year as a consultant once, which uses this approach, is Instana. And I guess you all have used some APM tooling in your life, and they all work similar. They go into your Java process too. They scan PIDs for Java processes. Then they install basically a general agent, look a bit around in the JVM what they need to do. And then they can load certain modules for supporting transactions in your code. For example, it might discover that you use a database by finding JDBC driver classes on your class path, and then will basically transform the methods that do the JDBC calls to measure the execution time it takes them. Right, and then you can extract all this data and generate traces and all so forth that you typically see on dashboards if you use an APM tool. Then also you can update these by just patching them, so they can just work in the background with you without you bothering about writing your app in a certain way or integrating against a specific API. Right. Just check how much time. Okay, halfway through. This is actually pretty good. Right. So how does this work? And ideally, in the long talk, I would start out now with giving you a tale of bytecode and how you can do it with tools like Asm, which is exciting. It's very insightful to do this once in your life if you find the time to actually manipulate bytecode directly, because you kind of get a grip of the essence of Java class files, and this is a gateway to understanding how the JVM works better. Because if you work with the OpenJDK code, for example, the OpenJDK code base, you need to understand how bytecode looks like and how classes are represented to find this entry into OpenJDK. But if you just want to write something that does something practical, it's often useful to use a more high-level API, and the library that I create, Byte Buddy, is trying to give you that. So with Byte Buddy, you basically just have a declarative DSL that tells you, or tells Byte Buddy what you want to do. And in this case, we tell Byte Buddy to find all classes that have a super type that is named my target user type. Then we want to transform this type to include a so-called advice to our hello world advice on every method that is just a method. So no constructors, just methods. And the hello world advice is now what we want to inline. As you can expect, hopefully, or it's the goal of the API to be intuitive at least, on every entry of a method in any subclass of my target user type, we will now print the line system out print in hello world as a first thing. And if you don't believe me that that works, I challenge you, of course, to copy paste this code, compile it, and add a manifest entry to this agent main class, attach it to any virtual machine that you want to, and you will seeing these hello world lines showing up. And you can take a JVM that has been running for a year. And of course, this is not useful again, this is a hello world example, but you can imagine what the advantage of something like this can be. If you have an application that misbehaves all of a sudden and you want to see what's going on, but you can't really kill the JVM because it's running in production and there's no fallover because it's an old system where this was a thing you did, then you can still try to extract logging data. And some frameworks have support for that actually, like Erin, for example, they are very aware of the bytecode it generates. So if you want to have logging, it's done by a Java agent that you have to attach so that it's not in normal code. So, and this has been proven useful to many people over the time, that you can actually look into running JVMs if you want to, right? So this works by basically just taking your user type, because user type is a subtype of user type, right? It's also going to be instrumented. So if there's a method foo, Byte Buddy will basically just take the advice code and inline it there. So we'll copy paste it to the target location, and now it's executed. So you have changed the running program to represent this new source file, right? You can also just say that you want to retransform existing classes. In this case, you will automatically pick up any class that has been loaded previously and retransform it once it's discovered, right? And that's as easy as I hope it should be, and it's still pretty performant. And I invite you, if you want to learn more about how to do this, just try it out. It should be that easy. All right. Of course, it's a very rich API advice. That's basically what you use for agent mainly. You can add method at the beginning of a method. You can also add method code at the end of a method. So Byte Buddy will do that. It will copy every return statement. Instead of returning, it will assign the value to a temporary variable on the stack, and then inline the exit code, and then return values. You can also access method arguments, for example, by just adding arguments to your advice as well, and then referencing them. So by adding a single argument to your enter advice of type value, string value, you can now access that. And then the actual code will still run as before. You can also change arguments. So if you want this method to print true bar instead of true, then this is the way you would do it, right? And now you can already think about implementing actual useful things, right? You can, for example, if you want to monitor the performance of something in a general manner, you can, for example, communicate a timestamp from the enter advice to the exit advice. And when you then receive this value in the exit advice and take the time again, you can subtract these two numbers and get the execution time of the method. And more or less, there's a lot of open source code that also is opening up for looking into how it's implemented. But I think Datadog uses Byte Buddy, and Instana uses Byte Buddy, and Stage Monitor uses Byte Buddy. They do nothing more than that, really. They basically implement this advice, right? And then they communicate the timestamp from the enter advice to the exit advice and measure execution time of a method. And then they can print it to a dashboard. And of course, there's a much more to it to actually make this data digestible, but the extraction mechanism is more or less that simple, right? All right, and there's a lot of properties that you can use to extract information of an advice method. and I won't go through all of them. I've done this in other talks on this topic, but it's in the Java docs, and I hope I have given you enough to self-educate from there. Right. I have 5 minutes left before we go into Q&A. So I'll just quickly run through class loader hierarchies, because when you develop agents, you will very quickly realize that that's the biggest frustration you have to face. Any JVM is composed of 3 class loaders: the boot class loader, loading Java lang string and so forth; the extension class loader, which was a mechanism to override things in the boot class path, barely used; and the system class loader, which is basically the class loader for the class path. And normal applications just work like this. Since Java 9, we have the platform class loader, because extension was rather obsolete, which allows now some extensions to JVM, like Java SQL modules and so forth, which aren't supposed to have core privileges. But of course, web servers, Tomcat, for example, uses these additional class loaders, and then you have OSGI, and you have people that implement custom class loaders, and those all create boundaries of visibility, because agents are always loaded on the system class loader, so you might not be able to access application classes. So when you want to write advice where you, for example, access HTTP request and HTTP response objects, which are types provided by Tomcat, then those types might not be available to your advice class. So when you write your advice here, HTTP client advice might not be loadable, because the system class loader does not know about HTTP client. Right? So in order to avoid this, Byte Buddy has a mechanism, again, to avoid this bias of class loading visibility boundaries. And so if you try this out and you want to write more ambitious apps, you should look into the advice mechanism for avoiding class issues, and then you just specify a string, and Byte Buddy will take care of the rest for you. So yeah. Let's see. So last point I can go through is self-attaching for Java agents, like as I suggested for Mockito. So how does this work? Well, you can self-attach by just finding out where you're currently placed. So you find your own PID, and fortunately, JVM has an API for that since Java 9. It's also possible before, it's much more complex. And then you just attach to your own jar file, which you can find out by the protection domain of your class loader. Then this agent, pseudo agent, just writes this instrumentation instance to some static, globally available field. Field should be static, of course. And then you can just read it from any location of your JVM, and Mockito does exactly that. So unfortunately, in Java 9, there was also added a restriction that you cannot self-attach anymore, but that's easily avoidable by just basically spinning up a new JVM process, which gets a new PID, and then you just use this additional process to attach back to yourself, because now the new PID is allowed to it again, and you're being able to do the same thing. But this is why, since Java 9, Mockito inline mock making takes about twice as long to start up. Yeah, but there's workarounds for everything. So with Byte Buddy, it's again a bit simpler. You just call Byte Buddy agent install, and you get an instance, so it does everything for you in the most efficient way possible. And you can also attach different APIs. So it requires the JDK attach module being available, which only is in the JDK. But I have made an effort to re-implement the entire attach API in native code based on JNA. So since Byte Buddy 1.9, you can entirely avoid the restrictions imposed by the JVM and just attach to any JVM, also on Hotspot and OpenJ9, but even on Solaris, I made it work. So yeah, you can try this out if you have an app that wants that as well. All right, and now it's 5 minutes to go. And we should start Q&A. Am I right there?
You are completely right. You are completely on time as well.
Yeah,
amazing.
Perfect.
Thank you. I appreciate that.
And I go to the last one. Yeah.
Yeah, we just leave that one up so that people can see that slide. I've got a couple of questions for you from both the Slido and the track or the Slack track. First one is, can two attached JVM agents have conflicts?
Yeah, absolutely. So what one agent can do is it can be implemented poorly and basically undo the transformations of the previous agent, which is of course, a bug in the agent, which often only gets discovered once you run two agents. Then it's up to finding out which agent is to blame. If you use Byte Buddy tries to be sensible for it, and it should work without any problems. There are exceptions if you hard code locations in your methods, for example. Then if the first agent transforms this method in a way that the second transformation doesn't work anymore, then of course it can still cause problems.
Yep. Is there a restriction on how many agents you can connect, or is that like as many as you basically want?
As long as you don't run out of memory for loading classes, you can.
Fair.
So there's obviously a limit, but yeah.
Can we also programmatically detach agents?
So an agent is done executing once the pre-main method or the agent main method is completed. So if you have then basically completed your business, then you're done anyways. If you want to basically undo the transformations you have applied, then Byte Buddy has an additional method on its own class file transformer implementation where you can just call .reset, and then all changes are reset. But you have to trigger it. It doesn't automatically happen after completing the pre-main or agent main.
Yeah, understand. If we look at, for instance, native images from GraalVM, can Java agents still be used?
Yes and no. So the general answer is no, but because there's no bytecode anymore, so you can't transform it. But there's an effort to implement an API that allows applying agents in build time, but it's not as mature as I would wish it was at this moment. But what you can do in Byte Buddy, it has a Maven and a Gradle plugin, so you can try at least for non-JVM classes. So everything that's a library or your own code, you can transform them during build time and then just native compile those.
In that case, yeah. A question over here, and I hope I read it out correctly. What kind of typical operation logic would make sense to be done with Java agents without incurring a significant performance penalty?
So typically it's performance monitoring tooling, and that basically it tries to be independent from the code base because it's developed by a different company and normally closed source. And security startups, for example, they try to build agents that automatically detect SQL injection. But of course, you have a minor, at a minimum, a minor performance penalty. But the good thing is that JVMs typically aren't at their executional limit. A lot of modern applications struggle with I/O, thanks to microservices. So there's a lot of CPU available. So as long as you don't use 100% CPU, then agents can be effectively neutral to your performance, unless you're CPU bound, which you typically are not.
So you basically use it for tooling that when you want to measure things, debug things, make sure that you intercept kind of things, that kind of. All right. One last question, and that is a question for me personally. When you can attach to a JVM, that might be a security risk, right? If you can connect to the machine and you can connect to the PID ID. You can potentially interfere with that. So how can you prevent this?
So you
from a programmer perspective, yeah. So
the API is considered safe from the OpenJDK point of view because only the same user, the same operating system user, is allowed to attach to JVM. That's secured by the attach mechanism. But the only real way, if you really want to prevent it for JVM, is to delete the socket file, and that's placed in a given location depending on operating system. And there's a bit of a different mechanism on Windows, for example, because they don't have Unix sockets, obviously. If you delete this file, it's effectively impossible to ever attach to JVM again. What you also can do is you can kill the attachment thread. So you can basically start an agent and then block the attachment thread forever. Then no agent will ever be able to use this thread again. But normally, if you came as far as being able to execute a program with the same operating system user on a physical machine, then if an attacker got that far, you already,
you are already screwed. But you don't want to know how many Docker containers are run by root, for instance. So All right, I'm gonna cut it off here. I want to thank you so much, Rafael, for this talk. I'm gonna unshare your screen so it's just the two of us, and